Okay, so in this part we are going to discuss about the frequency and the wavelengths of the X-ray. Okay, so frequency is nu, wavelength is lambda, and as it is a electromagnetic wave, C is equal to nu lambda in vacuum. Okay, so now if you look at the experimental setup, what was the experimental setup? Let me draw. This is some cathode ray like this, and there is a metal. The cathode ray collide with that metal and X-ray was emitting, right? Now there is a potential difference, plus minus, this is the potential difference here. Okay, due to that potential difference the cathode ray was generated and the electron was moving, right? So let's say the potential difference is V volt. Now the electron has the charge E, the charge of electron is E, so what will be the energy of that electron or cathode ray? The energy of the cathode ray is very high, right? That's why the X-ray was emitted. So energy of electron or cathode ray should be E times V, EV. This is the energy. Now having that EV energy, electron is going to collide with that metal and the X-ray was emitting. So we can say that if the total energy is transferred to the X-ray, that means X-ray is the electron is absorbed with that EV energy and the X-ray of that EV energy is generated. If it is the case, then we can say that total energy of X-ray is converted to the X-ray. So now in case of X-ray, what will be the energy? It should be h nu. Now we know, right, the Planck's law. So it should be the energy of X-ray should be what? Equals to h nu or hc by lambda. It should be. Now if the total energy of the electron is converted to the X-ray, energy of the X-ray, that then we can say that energy of the X-ray will be maximum. So E max should be EV. That means h nu max should be EV, or we can say that hc by lambda minimum, because if the frequency is maximum, it essentially means that the wavelength would be the minimum. So lambda mean will be hc by EV. So the X-ray emitting from that solid will have different types of lambda, different types of wavelength, but the minimum wavelength will be hc by EV. That depends on, we know h is constant, c is constant, e is constant, these all three things are constant, v is only variable. So v is the potential difference given by us, that is the experimental setup. So lambda mean will be inversely proportional to the voltage. Okay, so this is in our hand, we can fix it. So now if you put this value h, c and e, these are the constant, we know, I am not writing. H is the Planck's constant having the value 6.626 into 10 to the power minus 34 joule second. This is A. C is our speed of light 3 into 10 to the power 8, and E is our charge of the electron, which is 1.6 into 10 to the minus 19 coulomb. If you put it, then we obtain the lambda mean will be 1.243 into 10 to the power minus 6 divided by V in meter, because lambda is the wavelength, it should have the unit in meter, centimeter or Armstrong. So we can write it. Okay, so this is the unit. Now it totally depends on our voltage. You have to understand that if the voltage is greater than the when the V voltage is given, X-ray is emitting, right? The X-rays have the different kind of wavelengths. The maximum energy, the energy having that electron is EV. If the maximum energy is transferred to the X-ray, okay, then it will also have the energy EV, and that of that X-ray should have the minimum wavelength. If the less amount of energy will transferred to the X-ray, then obviously it will have the greater wavelength. Okay, so that's why it's the lambda minimum, which is 1243 by V nanometer, but this is in our hand because V is the variable, we have to choose it. So we are discussing about this lambda minimum, frequency and the wavelengths. So now if you put V, the voltage, applied voltage is 50 kilovolt kV, then lambda is lambda minimum, not lambda, 0.2486 angstrom. Okay, and if the voltage is, it's just mathematics, 10 kilovolt, then the lambda minimum would be 1.243 angstrom. So as much the voltage increases, lambda decreases, we can see from here. So what is the conclusion? Conclusion is, okay, so let me remain this. What is the conclusion? When the whole energy of an electron, what was the energy of the electron is EV, right, belonging to the cathode rays, because its electron, actually cathode is the flow of the electron, this energy is actually the energy of the cathode rays, is utilized to bombard the target to produce a photon. Photon means the X-ray, photon of the X-ray, because this discussion actually we are considering, we know the dual nature, we know the Planck's hypothesis, these things, right. So after that we are just doing these things, this was not known at that time. Okay, this now we are doing this. Okay, so photon, only then the wavelength of the X-ray becomes equal to the lambda mean, and as given in this equation. Okay, generally the whole energy is not converted, obviously whole energy will not be the converted. It is an ideal case. If the whole energy would be converted to the X-ray, then this will be the case, then the lambda will be the minimum, that is the lambda mean. Okay, converted into the energy of X-ray photon, and hence the wavelength becomes more than the lambda mean, as I discussed. For this, lambda mean is called the minimum wavelength of the X-ray. So that means in case of each X-ray, there should be a lambda minimum, right. From this experimental setup we can say this. If whole energy is not converted to the X-ray photon, then the energy will be less of that photon, obviously. So accordingly that we can know energy and wavelength inversely proportional, so should be the wavelength will be larger. Okay, so now if you increase the potential difference V, if you make it higher, then the wavelength will be, the lambda mean will be much smaller. We can see from here, if it is 50 kilovolt, then it is 0.2486 angstrom. If it is 10 kilovolt, it is 1.243 angstrom. So clearly it inversely proportional with the voltage potential gradient. Okay, so now if the what will happen if you give the high voltage, high potential difference, then the lambda mean will be less. It means the energy will be more. So if the energy will be more of that X-ray, it will have the more penetrating power. It can penetrate more thinner, more wider sheet, we can say that. If the energy of that X-ray is less, then it cannot penetrate much. If the energy of that X-ray is increased, if you increase that, then the penetrating power will also be increased. It can be seen from here also, because the lambda and the energy is inversely proportional. If lambda is decreasing, then energy will also increase. Okay, so this is the case. So now this V, the potential difference should be 10 to the power 6 volt to produce hard X-ray equivalent to the wavelength 0.01 angstrom. I am coming to that. What is there are two types of X-ray. One is the hard X-ray, another one is the soft X-ray. But before that, okay, the wavelengths of X-ray, these wavelengths, this lambdas wavelengths of X-ray is 1/1000 part of our visible light. Okay, because we have already discussed, right, the wavelength is very small. How small it is? It is 1/1000 times, that means 1000 times smaller compared to our visible light. In visible light, we know 400 nanometer to 700 nanometer, so 1000 times smaller. So you can understand it actually 4 angstrom to 7 angstrom like this. It's very very small, and now as the energy wavelength is small, so energy will be 1000 times more compared to our visible light. Okay, so this is observation. And the next one is the soft X-ray. We can classify X-ray according to the wavelength or the energy, and the hard X-ray, because from here we know that the lambda mean will depends on the V, so we can vary it. We can vary by varying our the potential gradient. So there are two kinds of X-ray, we can say soft X-ray and hard X-ray. What is the definition of soft X-ray and hard X-ray? So soft X-ray, when the lambda around 10 angstrom, because it's actually 4 to 7 approximately for X-ray. For X-ray in general we can say it actually 0.01 angstrom to 10 angstrom, the range is. So it's actually 1000 times smaller compared to our visible wavelength. So when it's very high, the wavelength is high, then the energy of the X-ray will be less. This is understandable. So when the lambda is comparable to the 10 angstrom, then actually the energy we can evaluate hc by lambda. If you put it here hc by lambda, then you obtain that the energy will be or 1.24 kilo electron volt. Okay, now in case of hard X-ray, if lambda is 0.01 angstrom, so clearly from, because it's linear, so energy would be 1.24 MeV, mega electron volt, thousands times more. Okay, so this energy is thousands times lesser compared to this energy. So this energy, as the energy is very less, so that's why this X-ray is called the soft X-ray. So soft X-ray has the energy wavelength around 10 angstrom, and hard X-ray have the energy around 0.01 angstrom. In between we can say there is a mix. Okay, 0.01 to 10 around. So if it is the scale 0.01 to 10, so around 10, so this is, we can say this is the our, sorry, so this is our soft X-ray. This is actually in lambda, this scale is lambda in angstrom. Okay, and here around that part, so this is actually our hard X-ray. In between we can't make distinguish. Okay, so this is soft X-ray and hard X-ray. Okay, hard X-ray has the higher energy, due to higher energy, as it has the higher energy, that's why it's called the hard X-ray. Okay, so this is our X-ray. Now what is the uses? We know very well, right? So now let me write it again. Uses of X-ray. Okay, so what was the uses? First, in medical science, we know that in radiography, X-ray are used for detection of our fractured bone or kidney stones, right? We did X-ray nowadays. It's very very common for us. So radiography is one of the case. Second is radiotherapy. Hard X-rays meaning the X-ray having the smaller wavelength or the higher energy. These are the hard X-rays. Hard X-rays are used in radiotherapy to destroy the cancer cells. Okay, so this is X-ray also used in case of radiotherapy. And another one is fluoroscopy. Okay, this is also an imaging technique, just like our radiography. Fluoroscopy is also an imaging technique. This is also used X-ray. This is actually used to take real-time moving images of the internal structure of our living body. So this is the moving images. okay, not the steady. This is the uses of X-ray in our medical science, medical cases. Now other important uses are X-ray are used to analyze the crystal structure. As I discussed earlier, that X-ray actually make the diffraction. When it interacts with the crystal structure of solid, it makes a diffraction. Okay, in that case there is a famous law, that's the Bragg's law, gives, which says that n lambda equals to 2d sin theta. Okay, this law actually guides how the X-ray will be diffracted. Okay, so this is not in our syllabus. So crystal structure to determine the, or to analyze the crystal structure, and also the metallurgy. In case of metallurgy, X-ray also used to detect the defects in metallic casting. So these are the uses of X-ray. So now this part actually now covered. Now the next, I'm going to the next part. So let me stop here in this part. Actually, in next part I will discuss about the X-ray and the atomic number. That is very, very important. Let me stop here. I will carry forward from here. So thank you for paying attention with me. So let's meet again in the next class. Thank you.